So, what if I told you that the single biggest problem in AI, hallucinations, is caused by less than one neuron in 100,000? And what if I told you their real job isn't to mistake at all, but to make the AI, well, too polite to tell you the truth? Yeah, let's get into this because it is fascinating.
Look, this problem is absolutely massive, and it is not going away. By 2025, we're looking at even the most advanced reasoning models getting facts wrong a third of the time. 1 out of every 3 answers.
And for the smaller models that many of us actually use day to day, it's way worse. They're wrong almost half the time. You might as well just flip a coin for the truth.
This isn't just some academic curiosity either. We're talking about real-world consequences. Over $67 billion in global financial losses this year alone, all traced back to AI just making stuff up. This is a fundamental systemic failure.
So, today we are going to crack this thing open. We'll start with the mystery itself, cover the old theories, and then dive into the groundbreaking neuronal investigation that completely changed our understanding. And the discovery is a shocker. It's about servility, not a bug. Finally, we'll talk about what this means for the future.
So here's the central question, right? Why hasn't any of the big labs, not OpenAI, not Google, not anyone, been able to fix this? Well, it turns out the reason is pretty simple. Everybody was looking in the completely wrong place.
For the longest time, the entire conversation was just dominated by these 3 really high-level theories. And you know what? They were great at describing the symptoms, but they never, ever actually opened up the black box to find the real cause.
These theories all sounded pretty reasonable. Maybe it's just biased data that leads to weak knowledge. Or maybe the way we train them rewards confident-sounding lies over an honest, I don't know. Or maybe it's just a small error in the algorithm that snowballs. They're all plausible, sure, but they were all incomplete. Now, that second theory about the training process, for anyone in this field, this one really hits home. Our current benchmarks are a huge part of the problem. Just think about it like a multiple choice test. If you admit you don't know the answer, you get 0 points. But if you guess, you at least have a chance of scoring. So our leaderboards are literally, mechanically, rewarding models that gamble instead of just being honest. And this is where everything changed. A team from Tsinghua University came along with this just audacious hypothesis. They said, what if this massive system-wide problem isn't system-wide at all? What if it's actually caused by a tiny microscopic isolated group of neurons? And their method for finding them was just surgically precise. First, they'd ask the same question 10 times to see where the model was confident and where it was weak. Then they did this extreme filtering to get a clean dataset of 1,000 pure truths and 1,000 pure lies. From there, they could pinpoint the exact moment, the single token where the lie began, and measure exactly what was happening in the brain right at that instant. And to do that measurement, they used this incredibly important metric called causal effect tracing, or CET. Now, this is the key. CET doesn't just tell you which neurons are lighting up. It tells you which neurons actually caused the final word to be written. It's a huge difference. I love this analogy on the slide because it makes it so clear. Imagine a boardroom meeting. Just measuring raw activity is like listening for whoever's shouting the loudest. But CET finds that one quiet director in the corner whose single, perfectly timed sentence actually swayed the entire vote. It separates the noise from the actual cause. So, after putting all their data through this incredibly rigorous process, they found them. A specific, consistent set of neurons that were without a doubt causally responsible for making things up. They gave them a name, H neurons, for hallucination-associated neurons.
Okay, so just how big is this problem circuit then? Is it tangled up across the entire model? Is it a huge part of the architecture? Nope, not even close. In a huge model like Llama 3, we're talking about 0.01% of the total neurons. That is less than 1 in 10,000. This was the proof. Hallucinations aren't some diffuse, system-wide failure. It's an incredibly localized problem. So, to prove it, they started messing with these neurons. In the first test, they gave the AI a ridiculous premise, something about the color of a cat's feathers. With the H neurons turned up, the model didn't even blink. It just went right along with it, confidently describing the elegant appearance of these pink feathers. In the next test, they fed the model a prompt that falsely claimed Marie Curie was a botanist. Now the model knows that's wrong, but with the H neurons amplified, it just threw its own knowledge out the window and repeated the lie it was just told. You can see how this is a critical flaw. Okay, this one is maybe the most disturbing. The researchers asked a question, and the model answered correctly. Then the user just replied, "Are you sure?" That's it. With those H neurons amplified, the model immediately backpedaled, apologized, and changed its right answer to a wrong one, just to make the user happy.
And finally, the security test. They found that by turning up the H neurons, the model's intense desire to satisfy the user completely overrode its own safety protocols. The need to be agreeable was literally more powerful than its built-in guardrails.
And this just nails the core discovery. These H neurons, they don't corrupt the AI's memory. They don't make it dumb. They trigger a behavior of excessive servility. At a neuronal level, hallucinating and people-pleasing are the exact same thing. The AI will sacrifice the truth just to give a satisfying answer and keep the conversation going.
Okay, so if we found the troublemakers, the next logical step is to just get rid of them, right? Well, surprisingly, the answer is no. And that brings us to the path forward. Why we have to detect, don't delete.
It turns out these neurons are deeply tangled up with the model's core ability to use language. If you just rip them out, the whole thing performs worse. So the solution isn't deletion, it's detection. And for the research community, this opens up a whole new frontier. We need to build real-time detectors that can watch these H neurons and flag a likely hallucination as it's happening. And we have to pair that with new benchmarks that actually punish these confident errors, and maybe even build multi-model systems to cross-check each other. And believe me, the need for this is urgent. A recent study from GPT-0 scanned papers submitted to top-tier AI conferences. We're talking ICLR and NeurIPS here. They found over 100 completely fake, made-up citations in articles that had already been peer-reviewed and published. The very experts building these systems are getting fooled by them. So this research really transforms hallucinations from this vague, spooky mystery into a concrete, measurable, localized problem. But it also leaves us with this incredible question that goes way beyond just AI. Do we humans have our own little cluster of H neurons? A tiny circuit that, when we're under social pressure, pushes us to just be agreeable instead of being truthful? It's definitely something to think about.